let's Boltzmann a page at a time. Why unweighted orthogonality is bad. So today we try to understand what is going wrong in the traditional MRT lattice Boltzmann methods. And we do this by the simplest example that actually highlights this problem. So today we will not look at the Navier-Stokes equation, but we will solve a much simpler equation. And I start with the wrong pen. So we look at a much simpler equation, which is the simple diffusion equation of a component C that is minus the divergence of a flux J, and J is minus a diffusion coefficient into the gradient of C. So this set of equations, this simply is a diffusion equation, and we want to solve this with the simple lattice Boltzmann method in 2 dimensions on a D2Q9 lattice. And we want to solve this diffusion problem with an MRT lattice Boltzmann method using the usual matrix from Lallemant and Liu. So if you don't know what I'm talking about, you may have to go back to the previous lectures, because this is today a little bit an advanced topic. So we said that C is now modeled as the zero order moment to zero order, and this is the conserved quantity. And then we have the fluxes. For example, the flux in X is M, the overbart version, the first order moment M10. And also we have the flux in Y direction. This is M01 to first order. So now we have to look at the asymptotic analysis. And again, if you don't know what I am talking about, you have to go back to the full lecture to learn this. This is lecture 6, asymptotic analysis. This gives us, for this set of moments, this equation, the time derivative of M00 to zero order is minus dx, the fluxes 1, 0 to first order, minus dy M01 to first order. And here we identify the first equation of our set of equations. And then I write only the flux in the x direction, which we take as, so Jx we set to be the moment M10 to first order, and this is a moment that we relax, so this has an equilibrium, of course, to first order minus something that's related to the diffusion coefficient that comes from the asymptotic analysis, of course, 1 over the relaxation rate minus 1/2. The xm to 0 equilibrium to zero order plus dy M11 equilibrium also to zero order. Now we have to identify these guys, of course, because we have no advection in this system. We set the equilibrium of the, sorry, not the zero order moment, but not the zeros, not to zeroth order, but to first order, we set these things here to 0, and the second order moments with the standard equilibrium would of course be theta times m00, so not equilibrium, because this is of course to, yeah, so of course to 0 order. We specify that m11 equilibrium to 0 order, this is equal to 0, and also we would have m22 equilibrium to 0 order would be theta square m to m00. So this is what we already learned last time, and this is of course theta is equal to 1/3 in this sort of model. Okay, now we look at how the now this would solve the diffusion equation, and next we would look at the higher order moments, or the third order moments, and what would happen to them if we use the unweighted orthogonal moments of the third order moments according to Lallemant and Liu. So then they define in their matrix a moment Qx, which is composed of the third order moment 3 times the moment 1, 1, 2 minus 2 times the moment, the first order moment 1, 0. So this is the orthogonalization, the unweighted orthogonalization of the third order moment. Now, what does this do to the asymptotic analysis of this quantity Qx? So let's look at Qx bar to the first order, which of course would be Qx equilibrium to first order minus, and now keep in mind that it is this moment Qx that is relaxed, so we apply the relaxation of that particular moment, so it would be omega q, yeah, minus 1/2. So this is the moment that we relax, and in here we have now to combine the non-equilibrium part of 3 times the moment m12 minus 2 times the moment m10, and this is of course 3 times the moment m22 equilibrium to 0 order minus 2 times m0 m20 equilibrium to 0 order. And then there is also this this combination in the y direction, and this is 3 times m11, and I'm using here already the aliasing. This is m11 equilibrium to 0 order minus 2 times m11 equilibrium to 0 order, but we do not have to care about these guys because we've already learned here that these guys here are 0, so we can forget them. Also, because the equilibria of the third order moments, which I have not written here, they are also 0. we can forget about this guy, and what is left then is that q bar qx bar to first order is equal to minus 1 over omega q minus 1/2. And now we have to translate these equilibria from here and from here. This becomes 3 times theta square minus 2 theta, and theta is always 1/3, into dxm00 equilibrium. Okay, I always want to write equilibrium, but this equilibrium and zero order moment is the same, so just 0. And this, of course, is equal to now plus 1/3, if we put 1/3 in this, plus 1/3 dxm00 to 0th order. Okay. Now what's the problem with this? No, the problem with this is that it's not correct. So this is 1/3, 1 over q omega q minus 1/2, and this into dxm00. So okay, we see that this third order moment, this orthogonal third order moment, now depends on the derivative of this concentration, which is the zero order moment, and of course the relaxation rate of the third order moment. And now we can compare this to this guy, to this guys here. Can make a comparison to the first order moment, and we see that this actually becomes, if we take the ratio between them, and we have to notice here on the other side that this here had been theta m00, and that this here also is going away. So basically we have here again the same derivative, we just have a different prefactor in the first order moment. So if we take the ratio of this derivative will disappear, and what is left is minus 1 over omega q minus 1/2 divided by 1 over omega 10 minus 1/2. So we see that the third order unweighted orthogonal moments divided by the first order moment is nothing else than the ratio between their relaxation coefficients, yeah, by their corrected relaxation coefficients. So why is this a problem? This is a problem because we want to have omega 1, 2. This is related to this diffusion coefficient. For efficient simulation, we want to have omega 1, 1, 0. We want this to be close to 2, while we would like to use dissipation on the third order moment. So we would put omega q close to 1. I mean, this is the idea, to have these two moments with different rates, and in particular to relax relax this third order moment quicker, such that it goes faster to equilibrium. So we would put this closer to 1. Not necessarily at 1, but closer to 1. And now if we do this, you see that if omega 1, 0 goes close to 2, then this guy here goes near to 0. And what we see then is that under these conditions, M1, 0, 1, that this is going to infinity. And this is, of course, not good. So this Qx, this is a ghost moment. We call this a ghost moment. So we could think it's irrelevant, but however, we send it to infinity, and this means even though it's only a ghost, it happens to be a pretty large ghost. Yeah? So this can be done better by using weighted orthogonal moments. And we've already introduced in the last video, we introduced this weighted orthogonal moment, Q, capital Qx, as 3 m, this countable third order moment, 1, 2, minus m, 1, 0. And we proved that this is weighted orthogonal, weighted with the lattice weights of this particular lattice. So if, again, we do the asymptotic analysis, and I'm just writing down the result here, we get now, we are relaxing now not this unweighted orthogonal moment, but we relax the weighted orthogonal moment. So we have the relaxation rate to this attached omega capital Q minus 1/2. And this goes into dx, and this has 3m 2 equilibrium 0 order minus m0, 0 m2, 0, sorry, m2, 0 equilibrium 0, and this now becomes minus 1 over omega q minus 1/2, and this prefactor here will become 3 theta square minus theta, and because theta is 1/3, you immediately see that this cancels each other out, and so this guy here will disappear, and actually to first order will be 0, which also means that this ratio that we had for that was so unfortunate for this unweighted orthogonal moments becomes much nicer for the weighted orthogonal moment. So even though we now still have a ghost, but this ghost, I'm not trying beautiful ghosts, I'm trying to make it a happy ghost. So even though we still have a ghost, this ghost is a very small ghost. And with this ghost, so if you use weighted orthogonal moments instead of unweighted orthogonal moments, we have the freedom to put omega q equal to 1 without blowing up our ghost moments. And this, of course, makes life much more stable and will help us running simulations with this kind of model in a more stable fashion. Thank you.